Hello students, very good afternoon. This is Mayur S. Murray, your chemistry tutor, as you all know. So we are covering a chapter called Ionic Equilibrium, and today we are into the sixth session of the chapter called Ionic Equilibrium. In the earlier session, we had seen the pH, pOH calculation. We had seen how different types of salt undergoes hydrolysis and all that. Okay, now we're gonna see what is buffer solution. I don't know, you might have heard about it or not, but buffer solution are the ones which helps maintain the pH, or I would say which helps maintain the acidity or alkalinity in so many products and in our blood also. Okay, so we're gonna see what is pH, how do we calculate the pH of the buffer solution and what actually are the buffer solution. Okay, so on that note, I welcome you all to JEE chemistry session number 6 for ionic equilibrium. Let's begin. So the buffer solution. Now what are buffer solution? See, it is a solution that resists the change in pH, value upon addition of small amount of strong acid or base. That means if you have one solution, okay, and if you do not want the pH of that solution to get changed, then what do? You add a buffer solution into that solution. For example, suppose if you have a pickle. Suppose if you have a pickle with you, okay, a mango pickle or any pickle for that matter. Okay, this is the bottle. This is where you have your pickle. Okay, now what do you want? You want the pH of this pickle solution to remain constant. Why? Because if it changes, if the pH of this pickle changes, it might ruin it, or I would say it might alter the taste of it. Or hi Kashi Fang Dian Gaming. Okay, hi, very good evening beta, very good evening. Your name is so difficult to read, so Kashi Fang Dian Gaming, that's what your name. Okay, so yeah, very good evening by the way. So if you want this pickle to maintain its pH or to maintain its acidity level or basicity level, what do? You put a buffer solution into it. So whenever you put a buffer solution into it, even if you add a small amount of acid into this pickle, or even if you add a small amount of base into it, the acidity or the pH or pOH of this pickle would never change. And that is what the buffer solution do. It is a solution which resists change in pH value upon addition of small amount of strong acid or strong base. Now generally less than 1%. It doesn't mean that if you put a whole bottle of acid into the pickle, obviously the pH is going to change. I am talking about if you add a small amount of acid or small amount of base into it, then it resists the change in pH, and then you call it as a buffer solution. Okay, or sometimes when the solution is diluted, then also it might change its pH, and that time also if it is resisting it, then it is called as buffer solution. Okay, so that is what the buffer solution is all about. Now what is mean by capacity of a buffer solution? See, the capacity of a buffer solution to resist alteration in its pH value is known as its buffer capacity. Now what is mean by that buffer capacity? See, if you add 1 ml or 10 ml of a solution of an acid into 1 liter of the buffer solution, then how much pH it is resisting the change? Then that is called as the capacity of a buffer solution. Okay, and this mechanism and this whole mechanism of buffer solution is called as buffer action. This whole mechanism is called as buffer action. So these are not something like a rocket science. It is just simple. Buffer solution is any solution. Buffer solution is any solution which resists change in pH upon addition of small amount of acid or base. Okay, that is what the buffer solution is all about. Obviously we're going to see the mechanism of it, how does it does that. Okay, but this is what the definition of buffer solution is all about. Okay, chalo. Now the next. Now, what are types of buffer solution? See, there are two types of buffer solution. One is simple buffer solution, the very simple buffer solution. Another is mixed buffer solution. Our discussion is mainly going to focus on mixed buffer solution only. But there is one more buffer solution that is called as simple buffer solution. And you should also know about it. That is why I am telling about you this simple buffer solution and mixed buffer solution. Okay, let's see what is a simple buffer solution first. Now, simple buffer solution is what? It is nothing but a salt of, it's a mixture, right? I would rather say it's a mixture of salt of weak acid and a weak base in water. For example, ammonium acetate. See, this is the salt. Okay, if you take this salt, what would it give you? It would give you CH3CO minus plus NH4 plus. Now, where do you think CH3CO minus or acetate ion came from? Or where do you think NH4 plus came from? Obviously, if you mix acetic acid, with NH4OH, if you mix acetic acid with NH4OH, then what will happen? Just a second. Oh, what is happening? Pain. Yes, here it is. I was not able to see. Yeah. So what happens here? This H from acetic acid and OH from ammonium acetate, sorry, ammonium hydroxide, both of them mixed together. What remains behind is CH3CO minus acetate ion plus NH4 plus. So both of them are combining, right? Both of them are combining to give you this ammonium acetate. So ammonium acetate basically is a salt of weak acid and weak base. When you take that salt and dissolve it into water, it gives you what? It gives you simple buffer solution. Now let me tell you what is the buffer action. What is the buffer action of this simple buffer solution? Let's see. Now let's take ammonium acetate. Now ammonium acetate is what? It's a salt, right? And I had told you earlier, you take any salt as you want. You take any salt as you want. Whatever kind of acid or whatever kind of base has it been made from, be it a strong acid, strong base, weak base, doesn't matter. If it's a salt, it will dissociate in water completely. Any salt in water dissociates completely. So we are taking ammonium acetate. Okay, how would it dissociate in water? It would give you CH3CO minus plus NH4 plus, right? These are the ions which it gives on dissociation. Now what do you do? On addition of an acid. What is acid? You take any acid, for example, HCl. Okay, now HCl will do what? HCl will do H plus ion. Now which ion would H plus ion combine with, you think? Your H plus would surely combine with this, right? And that would give you what? That would give you CH3COH. What is CH3COH? It's a weak acid. It's a weak acid, right? So as soon as it forms, it will not dissociate further. No dissociation or very less dissociation. No dissociation or very less dissociation. In other words, whatever H plus ion you added from H plus ion, that was captured or absorbed by acetate ion to give you acetic acid. And acetic acid is what? It's a weak acid. So being a weak acid, it will not dissociate further. So in other words, it has taken up that H plus ion. Now since it has taken up that H plus ion, what will happen? That means the acidity will not increase, because H plus ion is responsible for increasing the acidity. Now H plus ion has been absorbed by the acetate ion, and upon absorption it gives you weak acid. Weak acid doesn't dissociate, therefore H plus ion has gone, right? So that means that is the way by which it controls the pH, or I would say that is the way by which it does not let it increase the acidity. Okay, so that is when you add H plus ion. Okay, now the second case. What does happen on addition of NH4OH? Sorry, not NH4OH. Sorry, my bad. Take any base that you want. You can take any base. Suppose you take NaOH, a strong base. NaOH would give you what? It would give you OH minus. Now OH minus is having a negative charge. What ion you think would it combine with? It would combine with NH4 plus, isn't it? That is what it's going to combine, and it would give you what? It would give you NH4OH. Now NH4OH again is what? NH4OH is a weak base. So weak base, therefore it will not dissociate further. It will not dissociate further. Basically, whatever OH minus ion has been came from NaOH, all of those hydroxyl ion would be absorbed by NH4 plus, which will give you NH4OH, which is a weak base, and being a weak base, it will not dissociate further. In other words, whatever OH minus has came into system, which otherwise would have increased the basicity and consequently would have increased the pH also. Now that OH minus has been absorbed by NH4 plus to give a weak base. Being a weak base, it doesn't dissociate. Therefore, OH minus has been absorbed completely, and that is how it maintains the pH. That is what the buffer action of simple buffer solution is all about. Okay, I hope you must have understood it pretty well. If you really do, please like this video, comment on it, subscribe to Practical Live, or you can also comment if you have any doubt. Okay, chalo, let's move ahead with this now. So this is what the simple buffer solution is all about. Now we're gonna see what the next is. Okay, buffer action. I already told you what kind of buffer action is there. Okay, or you can see it once more. I tell you, you can take any other buffer solution. For example, if you take AgCN, or suppose you take NH4CN. Okay, now what would your NH4CN give you? NH4CN, it must have been made from HCN plus NH4OH. So it's a weak acid, weak base. It must have given you NH4CN plus water, right? Now your NH4CN would be dissociated as NH4 plus CN minus, right? Now if you put the H plus ion into this from the outside, this is your system. If you add H plus ion into this system, it would give you what? It would give you HCN. Now this HCN will not dissociate further. No dissociation. it will not dissociate further. So since it doesn't dissociate further, therefore H plus ion has actually gone. Similarly, if you add OH minus, again OH minus would be absorbed by NH4 plus, that would give you NH4OH. NH4OH, again it's a weak base, it will show you no dissociation. That is how the added H plus and OH minus ion gets absorbed by the given system. Okay, that is how the simple buffer solution maintains the pH. Okay, now we're gonna see the mixed buffer solution. Okay, I hope this must have been pretty much helpful for you to understand how does the buffer actually behaves. So the next is mixed buffer solution. Okay, mixed buffer solution. Now mixed buffer solution, there are two types of mixed buffer solution. Simple, one is acidic buffer, another is basic buffer, as per the name suggests. Acidic buffer, basic buffer. Now don't get confused here. Don't get confused here. Is that when you have an acidic buffer, that means it maintains the acidity and it doesn't think about the basicity? No, it's not like that. You take acidic buffer, you take basic buffer, doesn't matter. Both the types of buffer will always help you maintain the acidity as well as basicity. Both the types of buffer always help you maintain the pH. Now, when you are maintaining the pH, it is obvious that pOH also gets maintained. It's not like that pH, you are controlling the pH and pOH is getting altered. No. If you are maintaining the pH, pOH automatically gets maintained. Okay. So now let's see what is an acidic buffer. See, the acidic buffer. What is acidic buffer? Acidic buffer solution consists of a solution, is basically mixture of a weak acid and its salt with a strong base. Is basically a mixture of a weak acid and its salt with a strong base. It's like that. Okay, it's a mixture of a weak acid and its salt with a strong base. What is the best example? Sodium acetate. What I'm saying, it is the mixture of, let me tell you once more, it is the mixture of weak acid plus its salt. Whose salt? Weak acid's salt. Its salt with strong base. So if you take, so basically acidic buffer means what? If I give you example here, acidic buffer is a mixture of weak acid. What weak acid we take here is acetic acid. CH3COH, that's your acid, plus acidic acid salt with a strong base. Now this is your acidic acid CH3COH, and if you mix it with a strong base, for example NaOH, what would happen? This H plus ion, this OH minus ion, together they will give you water, and CH3CO plus Na, that will give you what? CH3CO minus Na plus. Sodium acetate, that is what we called as sodium acetate. So this is the salt. This is the salt of weak acid and strong base. Well, we had seen it earlier. So basically acidic buffer is what? Acidic buffer is a mixture of a weak acid and its salt with a strong base. So this is the weak acid, acidic acid. Its salt with a strong base is what? Sodium acetate, right? So that is what we're gonna add here. CH3COONA. So this is what an acidic buffer is all about. Let me give you some other examples also. Suppose if you take a weak base, any weak base, for example HCl. HCN is a weak base, right? Now this, as I told you again, acidic buffer is a mixture of weak acid and its salt with a strong base. So this is the weak acid plus its salt. Similarly, HCN is a weak acid and HCN will be combining with the weak strong base, which is NaOH. So this NaCN, it will give you, water will come out here and you will get NaCN. So HCN plus NaCN. This is a second example of a acidic buffer. Okay. Do you see any other example? Let me give you a classic example of it. Weak acid, that is H2CO3 plus H2CO3 plus NaHCO3. H2CO3 plus NaHCO3. This is also a weak acid and salt with the weak acid and salt with the strong base NaOH. So this is the buffer which our blood, this is the buffer which our blood uses. This is the buffer I was referring earlier. This is the buffer which our blood uses to maintain its pH level. Okay, so that is how this is actually being used. Now let's see how its action, how does this buffer solution actually works. Okay, so I had shown you different types of buffer solution, acidic buffer, different acids, their salt. Okay, all of these three, this one and this one, all of these three are acidic buffer only, and the buffer which I shown you last is the buffer used by our blood to maintain the pH level in our body. Now we're gonna see how does this buffer solution maintains the pH. Now for that we need to take the simple example, the one we saw at the first, that is what we're gonna use. Okay, so this buffer solution, CH3 COH. Okay, now CH3COH is what? It's a weak acid. Okay, so being a weak acid, it will dissociate partially, isn't it? It would give you CH3CO minus plus H plus, right? Because it's a weak acid. Now CH3CONA. CH3CONA, what is it? It's a salt, and salt, I told you, you take any salt, it will dissociate completely. So it would give you CH3CO minus plus Na plus. So these are the ions. These are the ions you have in your acidic buffer medium. Okay, now firstly, suppose you are adding acid into it. So adding H plus ion means what? Acid, right? Adding H plus ion into it, what would it happen? So as soon as you add H plus ion into this, what would it combine with? That H plus ion would then combine with CH3CO minus, right? And CH3CO minus on combining with H plus ion will give you what? CH3COH. Now what is CH3COH? It's a weak acid. So being a weak acid, it will not show you any dissociation further. No dissociation. So basically, whatever H plus ion you have added into system has been absorbed by acetate ion. Now acetate ion, whenever it combines with H plus ion, it gives you acetic acid. Acetic acid is a weak acid. So once it combines with H plus ion, it forms a weak acid, and weak acid thereafter shows no dissociation. That means your H plus ion has gone. Now that H plus ion would not show any effect on its acidity. Okay, sure. So that is the effect when you add H plus ion. That is how it maintains its pH. Secondly, addition of OH minus. If you add OH minus from the NaOH, what would happen when you add OH minus in the system? Whenever you add OH minus into system, there are two ions with which OH minus can combine with. Your OH minus can combine with H plus, your OH minus can combine with Na plus. But if it combines with Na plus, what would it give you? On combining with Na plus, it would give you NaOH, isn't it? And NaOH is what? NaOH is a strong base. So therefore, as soon as it forms, it will dissociate immediately. It will dissociate immediately. Therefore, in other words, if you see, it is like that OH minus doesn't combine with Na plus at all. Because even if it combines, it is going to give you NaOH, Na plus and OH minus once again, right? So therefore, your OH minus that has been added from external agency, that means addition of a small amount of a base, right? That is what added the OH minus here now. So that OH minus would not combine with Na plus, it would combine with H plus. Why? Because H plus ion on combining with OH minus would give you what? Water. And you know that water doesn't dissociate at all, or even if it dissociates, it's a very less dissociation. Water is surely dissociating less than the acetic acid. If I'm saying that acetic acid is dissociating very less, what about the water? Water is surely no dissociation. You know that even if it dissociates, it's very less. 1 into 10 raised to minus 7, that's very less. Okay, and that is why I'm saying that H plus ion on combination with OH minus, it gives you water. Water gives you no dissociation. So in other words, whatever OH minus has been added into the buffer solution has been absorbed by the H plus ion to give the water, and therefore the base. So therefore the added OH minus would not alter the basicity of this buffer solution. That is what the whole action of acidic buffer is all about. Okay, I hope you must have understood it pretty well. If you have any doubt regarding this, you can ask me in the comment section. Okay, chalo, moving ahead with this. Now the next part is pH of an acidic buffer. How to calculate the pH of an acidic buffer solution? That is called as Henderson equation. Actually, it's a Henderson-Hasselbalch equation, okay? But in many books, it has been referred as a Henderson equation only, okay? So let's see now. Now let's consider the acetic acid that we took, CH3. Let me write the acidic buffer first. So this is your acidic buffer, CH3COH plus CH3CONA, right? Now let's suppose that acetate ion CH3CO minus is represented as A, okay? Then what do we have? It's a HA, right? H stands for H plus, A minus, and this is A, no? So what do we have? NaA, right? Now HA is what? HA is acetic acid, right? How does it dissociates? It's a weak acid, right? So it will be dissociated as H plus plus A minus, okay? That is how it will be dissociated as. And your salt, CH3CONA, that is your salt. Now the salt will dissociate completely. Why? I told you earlier, salts are strongest electrolytes. Salts are the strongest electrolytes. Every salt, I'm not saying every, 99% of the salts dissociates completely. Okay, so that would give you CH3 CO minus plus Na plus. Okay, now this is HA, H plus A minus. So we need to consider Ka, right? What is Ka? Acid dissociation constant. What do we have after this? Okay, the same equation. Okay, yeah. So Ka is equal to H plus ion A minus divided by concentration of Ha, right? Ka is equal to H plus A minus divided by concentration of Ha. Now we need to find out what? We need to find out the pH. So to get the pH, what is the formula of pH? pH is equal to negative logarithm of H plus ion, right? So negative logarithm of H plus ion, that means what? We need to get this H plus ion outside of this. So H plus ion is equal to Ka, right? Ka into Ha divided by A minus, right? Now what do you do? Taking the negative logarithm of whole equation, because taking negative logarithm of H plus ion is going to give us the pH, right? So minus log of Ka into Ha divided by A minus, that will give us the pH for this. Now let me have the place on this side. Yeah, so minus log of H plus is what? Minus log of H plus is equal to your pH. Now minus log of Ka, right, plus into bracket minus log of Ha, right, then minus log of A minus, right? That is how you maintain it. Now minus log of K is what? Minus log of Ka is equal to pKa, isn't it? Minus log of Ka is pKa, minus log of Kb is pKb. We had seen it so many times, right? Now what do we have on this side? You have a minus log of Ha. This minus becomes what? Plus. So you have a minus log of Ha plus log of A minus. Minus become plus. So ultimately, on simplification, pH is equal to pKa plus log of A minus log of Ha, right? Which ultimately gives you, therefore pH is equal to pKa plus log of A minus divided by log of Ha, right? Now what is A minus? Look at here. A minus is what? H plus A minus, basically is acetate ion. See, A minus. This is also A minus, no? You take a NaA, no? This is NaA. So this is Na plus, this is A minus. So A minus basically is the what? A minus basically is the concentration of salt. And what is Ha? Ha is the concentration of your acid. And therefore, your formula becomes pH is equal to pKa plus log of salt upon acid. Log of salt upon acid. That is what the pH is all about. That is how you can calculate the pH of a acidic buffer. So basically, so this is called as Henderson-Hasselbalch equation. This is called as Henderson-Hasselbalch equation. Basically, pH of an acidic buffer is equal to pH is equal to pK plus log of salt upon acid. It is as simple as that. Okay, chalo. Moving ahead. Now let's see some of the significance of this acidic buffer. Okay. Range of an acidic buffer. So the formula, as you can see here, pH is equal to pKa plus log of salt upon acid, right? Now the ratio of salt upon acid, if the ratio of salt upon acid is equal to 0.1. If the ratio is 0.1, then what do we have? Then we have pH is equal to pKa plus log of 0.1. So basically, concentration of acid here, concentration of added acid is 10 times. You can see here, salt upon acid, it's 1 by 10. So 1 by 10 is 0.1. Okay, log of 0.1 is what? Log of 0.1 is -1. So pKa -1. That is the range. Okay, that is the range on lower side. Now upper side. Suppose the ratio of salt upon acid, is 10, then what do we have? Then pH is equal to pKa plus log of 10, right? What is log of 10? Log of 10 is equal to 1. So pKa plus 1. So pKa plus 1, pKa -1. Here what happened? Here the concentration of added acid is what? Is less than 10 times. I would say the concentration of salt is 10 times the concentration of acid here. So it's basically 10 by 1. Here it's a 10 by 1. So therefore, pH range here is equal to what? It's a pKa plus minus 1. That is what the range of acidic buffer is all about. That is your pH range. pKa is equal to plus minus 1. That is what the range I was talking about. It is either pKa plus 1 or either it's pKa minus 1. It cannot go beyond that. And the maximum pH range or the maximum limit of an acidic buffer, is what? See, if suppose concentration of salt and concentration of acid is same, if the concentration of salt and concentration of acid is same, then your pH will be equal to pKa plus log of 1, right? When the concentration of salt and concentration of acid is 1, it is log of 1. And what is log of 1? Log of 1 is 0. So that is the maximum. That is the maximum limit of an acidic buffer, beyond which it cannot act. Okay. So 0.1, 10 raised to 1 and 1. These are the limits by which within your acidic buffer actually can behave. Okay, chalo, I hope you must have understood this pretty well. Okay, chalo, moving ahead. Now the second, basic buffer. Now what is basic buffer? See, there is no difference between acidic buffer and basic buffer. Only thing is that in acidic buffer you took the mixture of a weak acid and its salt with a strong base. Here it's a mixture of a weak base and its salt with a strong acid. As simple as that. So here basic buffer is a mixture. Basic buffer is a mixture of weak base and its salt with a strong acid. As simple as that. So basic buffer is a mixture of a weak base and its salt with a strong acid. The base known example is NH4OH and NH4Cl. Now see again your basic buffer. So as I told you, it's a mixture of a weak base. Weak base, what weak base you took? NH4OH is a weak base. Okay. Now you want to form a salt out of it. How do you form a salt out of it? So NH4OH plus HCl. So this OH and this H plus ion together they gives you water, right? What remains is NH4 plus Cl minus. So both of this will give you NH4Cl. So NH4Cl is the salt of weak base and strong acid. So basic buffer is a mixture of that NH4OH and NH4Cl. Okay, that is how it's being added. So that's the basic buffer. Now we can have a different example apart from this, but we need to search for a weak base then, and there are very less weak bases. Okay, so let's consider this to be the best example of a basic buffer. NH4 which is a weak base and NH4Cl is an salt, it's salt with a strong acid, that is HCl. Okay, now let's see how does this basic buffer behaves. Let's see its mechanism, or I would rather call it as its action. Okay, so again NH4OH is a weak base, so it will dissociate to give you, it will dissociate reversibly to give you NH4 plus OH minus, right? NH4Cl is what? NH4Cl is a salt, so it will dissociate completely to give you NH4 plus Cl minus. Okay, now let's see how does it act. Okay, firstly suppose you are adding an acid. Okay, addition of an acid. So you are adding acid would release H plus ion you are adding here. Now where do you think H plus ion would combine with? If your H plus ion combines with Cl minus, what would it give you? It would give you HCl, and HCl is a strong acid, so it will dissociate again to give you H plus ion. So basically Cl minus which is present there, it's not doing any role. The Cl minus present there is not doing any role of maintaining the pH of this solution, because even if the H plus ion combines with Cl minus, it would give rise to stronger acid which is HCl, which has to dissociate once again. So better it doesn't combine with it, right? So what will happen? It doesn't combine with H plus ion, rather your H plus ion combines with OH minus. It combines with OH minus and it gives you what? It gives you water. Now water, you know that. Now since this H plus ion has combined with OH minus to give you water, obviously water is not going to dissociate again. So that means whatever acid you have added here has been combined completely or has been absorbed completely, and that is how it will not then alter the pH of this solution. Okay, so that is how it maintains the pH when H plus ion is added. Now suppose if I am adding a base, addition of a base, that means what? NaOH. Suppose you are adding a NaOH into this solution and you are adding what? OH minus. So what you think OH minus would combine with? There's only one ion with which it can combine with, right? Because OH minus having a negative charge, it would combine with NH4 plus only. Combining with NH4 plus, it will give you what? NH4OH. NH4OH is a weak base, so it will not show you any dissociation thereafter. So in other words, OH minus that you have added combines with NH4 plus has got disappear. I would say it got absorbed completely, because it is going to give you, or it is going to form a weak base, and weak base doesn't dissociate that much. That means the effect of added OH minus has been nullified, and that is how the basic buffer maintains the pH. That is the way by which the basic buffer maintains the pH. Okay. So I hope you must have understood this pretty well, how both acidic buffer and basic buffer maintains the pH of an solution whenever you add the small amount of H plus ion or small amount of OH minus. Okay. Chalo, moving ahead. Now we're going to see the pOH of a basic buffer, or you can say pH of a basic buffer, doesn't matter. Okay. So pH of a buffer solution, basic buffer solution. Okay. So yeah, again we're going to go by same mechanism. What mechanism? NH4OH, weak base, it will dissociate as, now let's consider NH4 plus ammonium ion, no? So again this is also A, right? So AOH, and okay, let me write it once again. So NH4OH plus you have what? NH4Cl. Okay, so NH4 plus, let's named NH4 plus, it's an ammonium ion, right? So let's suppose we are naming it as A only. Okay, so this is AOH and this is ACl. Okay, now NH4OH is a weak base. Oh, what did I do? Yeah, so AOH being a weak base, it will dissociate as what? A plus OH minus. Okay, and ACl or NH4Cl, that's being a salt, it will dissociate completely to give you A plus and Cl minus. Okay, now this is a base, weak base. For a base, what do we write? We write the Kb, right? Kb is equal to concentration of A plus multiplied by concentration of OH minus divided by concentration of AOH, right? Now to get the pOH, see, you need to find out the pH, okay? But there is no problem even if you find out the pOH first, because if you get the pOH, from pOH you can always get the pH, right? Because we know the formula pH plus pOH is equal to 14. Therefore, if you want to find out the pH of this solution, you need to find out the pOH, then putting the pOH into this value, you will get your pH. It is simple formula, right? So yeah. So taking OH minus concentration or rearranging this equation, what do we have is Kb into concentration of a weak base divided by A plus. Now again what do you do? Taking the negative logarithm of OH minus is equal to negative logarithm of KB into AOH divided by A plus, right? So yeah, so negative logarithm of OH minus, that will give you what? That would give you POH, that is equal to minus log of KB minus log of AOH, and minus minus I would say plus only. Now we had seen how does it ultimately changes, plus log of A plus. So POH minus log of KB is what? It's a PKB, right? Just like minus log of K is equal to PK, just like that minus log of KB is PKB plus log of A plus minus log of AOH. So therefore POH is equal to PKB plus log of concentration of A plus divided by concentration of AOH. Now do you see what is the concentration of A plus? Look at this. This is a salt, right? Concentration of A plus actually came from salt, and salt being a strong electrolyte, here it will dissociate completely. So therefore A plus is nothing but the concentration of salt, right? And what is AOH? AOH is the concentration of a base. You can see it here. And therefore POH is equal to PKB plus log of concentration of a salt divided by concentration of a base. It is simply or just like the pH calculation of acidic buffer, no difference, exactly same. There we find out the pH of an acidic buffer. So it was a pH is equal to pK plus log of salt divided by concentration of acid. Similarly here POH is equal to pKb plus log of concentration of salt divided by concentration of a base. So once we get the POH, from that we can easily calculate the pH. Okay, there is no anything difference in that. And here also the range that we had seen there, remember the range of acidic buffer plus minus 1, it that all the things that we had seen there, all those things are applicable here also. There is no change, exactly same. Okay, so I hope you must have understood this very well. If you really do, please like this video, comment on it. If you have any doubt with this, and please subscribe to Practical Live on YouTube. You can also subscribe our new channel, that is Practically 11 and 12, where you want to see exclusive the content of JEE and NEET for 11th and 12th. The link is in the description. Okay, now we had seen the pH calculation, how we derived the pH for acidic and basic buffer. Now let's see some of the numericals based on it. Okay, there's a buffer capacity also, but I don't think it is that important to tell you what is buffer capacity, because the definition is not as such complicated. What is it? It is defined as the number of moles of an acid or a base required. It is defined as the number of moles of an acid or base required by 1 liter of a buffer solution for changing its pH by 1 unit. That means if you want to change, as I told you earlier, the buffer solution does not let its pH change when you add a small amount of acid or base into it. But what happens if you add a large quantity of an acid or base into buffer solution? Then surely its pH is going to change, right? Because there is some limit for everything now. So if you want to change the pH of your buffer solution by 1 unit. If you want to change the pH of your buffer solution by 1 unit, it could be increasing the pH by 1 unit or it could be decreasing the pH by 1 unit. So to do that, how much amount of acid or base you need to add in the given buffer solution, and that is called as the buffer capacity. So basically buffer capacity is defined as the ratio. It is the ratio of number of moles of acid or bases added per liter divided by change in pH. So basically buffer capacity is the ratio of number of moles of acid or bases added per liter and of the change in pH. That is what it is all about. Okay. Now let's see we'll solve the one numerical and then we'll finish this session. Okay. So yeah, what is this numerical? So this numerical says how much volume of 0.2 molar solution of acetic acid should be added to 1000 ml of 0.2 molar solution of sodium acetate to prepare a buffer solution of pH 6, and pKa for this solution is also given. So basically the pH of buffer solution is given there. Okay, let me tell you what it is. Whenever the question like this comes, this might confuse you a lot. So what you do first is that just write the formula pH. This is acidic buffer, that's for sure, right? Because they have given an acetic acid, and acetic acid comes only in an acidic buffer. So pH is equal to pKa plus log of concentration of salt divided by concentration of acid, right? Now pH is 6, pK is 4. So these things are given, 6 plus 4.74. Now what have they asked? How much volume of 0.2 molar solution of acetic acid? That means this is what they are asking. So other things you will find immediately there, plus log of salt upon acid. Okay, so 6 minus 4.74 is equal to log of salt upon acid. 6.474 is what? It's a 1.26. 1.26 is equal to log of salt upon acid, right? So now what do? You need to send log to this side. So when you are sending log to that side, you will get the ratio of concentration of salt upon acid. So basically that's a antilog of 1.26. Now let me tell you what is meant by this antilog. Antilog means nothing but this value will become the power of 10. So this basically is equal to 10 raised to 1.26, and 10 raised to 1.26 is nothing but what? It is equal to 10 raised to 1 multiplied by 10 raised to 0.6, right? You must have understood or you must have learned all of this in mathematics, right? So 10 raised to 1 is 10 only, right? And 10 raised to 0.26, 10 raised to 0.26 is nothing but 1.82. So that makes this equal to 18.2. So 10 raised to, or I would say the antilog of 1.26 is equal to 18.2. Okay. So salt upon acid. So now here the salt upon acid is equal to 18.2. Now we need to find out the concentration of acid here. Basically the pH is already put here. To make this pH 6, how much acid we should be adding into this solution? That is what the question is all about. Because concentration of salt is also given. See here. And this is what concentration, it's number of moles, right? So how to find out the number of moles of salt now? What is salt? Sodium acetate, isn't it? Your sodium acetate is a salt here. And remember acidic buffer? Acidic buffer is a mixture of this acetic acid plus sodium acetate. Now, how to get the number of moles of sodium acetate? What is the formula? Formula is equal for number of moles is equal to molarity divided by number of moles and by V into 1000, right? We are getting N, no? So N is equal to M into V divided by 1000. So what is M? 0.2, right there. What is V? 100 ml, right? Divided by 1000 is going to become always there. 0, 0, 0, 0. 0.2 divided by 10, it will be equal to 0.02, right? So concentration of salt we got 0.02, but concentration of acid is still yet to be found out, but we don't know how much it is. So how much volume they are asking, right? So suppose VML. Let me change the color here so that you can see it clearly. Suppose VML of 0.2 molar acetic acid is added, then its number of moles will be equal to, again, what? Molarity multiplied by VML divided by 1000, right? Just like that, molarity is 0.2 multiplied by V divided by 1000, right? Substituting that value here, what do we get? The concentration of salt is 0.02, we just saw here, right? So 0.02 divided by 0.2 into V divided by 1000 is equal to 18.2, right? Now I don't have a space here. Okay, so I don't have a space here, so I will rub this down. I hope you have understood this, whatever calculation I have done it. Okay, I'll rub this space here. If you want to see it, you can pause and you can go back. No problem with that, okay? You can go back and you can always check that. So 1000 goes above, what do we get? 20 divided by 0.2 into V is equal to 18.2, right? Then what do we get? 20 divided by 0.2 is what? 20 divided by 0.2 is 100. 100 divided by V is equal to 18.2, and therefore V is equal to 100 divided by 18.2. Now 100 divided by 18.2 is how much? 1000 divided by 182, 5 185 900, 910, you got 90, 0. Again 18 5 somewhere around this, so 5.5. So therefore V is equal to 5.5 ml. So 5.5 ml of 0.2 molar acetic acid should be added to prepare a buffer solution of pH 6. Okay, now pH 6 means what? Now that buffer will maintain the pH of 6 plus minus 6. It might go to plus 7, it might go to plus 5, but not beyond that. Okay, so this much amount of volume you can add. So that is how you can solve the numerical based on it. Now we're going to see lots of numerical of such kind in the upcoming session. Okay, but for now that's it for the buffer solution. If you want to know more, please subscribe to Practical Live. You can also on YouTube. You can also download our app from a Google Play Store, from Apple Store. You can subscribe, you can download our channel, you can log into it, you can check a different courses in a Vedic maths, coding, chess, robotics, Python, Pro Python, okay? And we're gonna bring up the very new courses in that app also. And very recently we have added an app called Scan Anything, where you can scan any object and you can obtain the information out of it. It's very interesting. But for you to check that, you need to download our app. Okay, and also you can also subscribe to our new channel, YouTube, that is practically 11 and 12th. Okay, the link is in the description. So that's it for today's lecture. Bye bye from my side.